Hey, what's up everyone and welcome to Daily Code Buffer. In this video of scalable thinking, we are going to learn about the Paxos algorithm for leader election. So before we understand that, let's understand why we need the leader election algorithm and where it is being used. So let's consider we are building a system designed for storing the data into a database. So suppose consider that this is a client and client is connecting to a server and then server is connecting to database. So let me just say this is a client, this is server, which means this is your application and this is your DB. Okay, so now what you are trying to build is you are trying to build a scalable application where whatever the data comes from your client, whatever the application would be, it may be social media application, maybe school management system, library management system, whatever it is. So you are taking the data from the client, server is processing the data and it is saving the data into your database. Great. Now what happens if your database is corrupted or database lost the connectivity with your server? In this case, what will happen is your client will not be able to save the data from your server. So server will accept the client request, but it will not be able to store the data into your database. And it will be a really bad experience for your clients as well. And you will not be able to serve the actual function of your application, which is very bad for you. So how do we maintain this? We maintain this using the replication of the database, right? So what we try to do is we will add the databases. Suppose I'm adding one database, I'm adding one more database. Okay, and your application will connect through it. Okay, so now what I'm trying to do is I am having multiple database within my system so that if one of the database server fails, then also I'm able to serve the traffic via the rest of the database. So I'm trying to have the replication within my database. The same goes with your server as well. So what you will do is you will have multiple servers within your application as well. So that means that you are trying to have the scaling, horizontal scaling of your application. That means that you are having multiple servers to have your traffics served via the client, and you're also having the multiple databases to save the data as well. Now, whenever you are trying to have the multiple databases, what you are trying to do is you are trying to have the replication across the multiple databases. So suppose your database 1, okay, database 1 has 100 records saved. Great. Your database 1, that is your extra database that we have added, that has suppose 50 records saved, and this has suppose 40 records saved. Okay, so in this case what you have to do is you have to make sure that all the data is consistent available within your network of the database. So that means that all the database should have the same number of records. You cannot have like, okay, database 1 has some records, database 2 has some records, and database 3 has some records. We need to make sure that all the database has similar kind of data so that whenever I want to fetch data, I can connect to any of the servers and can get the data out of it. So that means that I have to do the replication. For doing the replication, what we can do is there are multiple strategies. One of the strategies is leader and follower. That means that one of the node out of all the nodes available within the cluster would be a leader. So suppose this is a leader, and this leader, what it will do is it will send the data to all the different servers that, okay, I'm having this data, replicate yourself, that keep the copy of this data within yourself as well. Okay, so that is a leader, and these are the followers that following the instructions of the leader. So this is the architecture which is followed when you are doing the database replication within your distributed system. Now how this leader and follower communicate with each other so that the leader is able to send the data to the followers, and if this leader dies, who will be the next leader, and how that particular leader will send the data to rest of the systems. Okay, so to understand this, we are going to understand the Paxos algorithm. Okay, Paxos algorithm was introduced by Leslie Lamport in 1989. And he has also introduced TLA Plus as well, which helps to build the scalable distributed databases. Cosmos DB is one of the databases which uses TLA Plus to build the system, and he has also won an Turing Award for computer science. So he's a famous personality for building Paxos and TL+. So in this video, we will learn about the Paxos algorithm, how it works, and what are the advantages and disadvantages of Paxos are. And we also understood that in which scenario leader election, when we are trying to have the database replication, how the leader and follower algorithm is been useful and how Paxos can be helpful here. Okay, so with this background, let's understand how the Paxos algorithm works. So Paxos algorithm works on two principles, that is two steps. One is prepare phase and second is the accept phase. Let's understand this with simple example, that you are a group of friends, okay? You are a group of 5 friends and you all are meeting in the evening to decide what to do in the night. So now you went to meet your friends, and then while meeting the friends you say, hey, what's happening everyone? So that means that you are asking everyone that, hey, what's happening? So that means you are trying to get the acknowledgement from each and everyone within your group that, hey, what's happening? Where are we going? What's the plan, right? So that means you are preparing everyone to have the answers about what's the plan of the tonight. So that is the prepare phase. That means you are preparing each and everyone about what's happening. Okay. Now, if so everyone says that, hey, nothing is happening, we still have to decide what to do, then okay, then what you do is, okay, nothing has been decided yet, let me be a leader and let me decide what to do. Then you try to be a leader and decide that, okay, let's everyone go for a movie. Okay, so that means that you are now giving instruction for everyone else to accept. So that means that's the accept phase. That means that you are asking for a movie. Great. Now out of each and everyone, okay, suppose 5 members are there. Out of the 5 members, 3 of them agreed that, okay, let's go for a movie. Great. That means that majority of the people said that, okay, let's go for a movie. So they acknowledged your first decision, what's happening within the team, what's happening within the group, and then they also acknowledge that whatever you proposed, that let's go for a movie, everyone agreed that, okay, let's go for a movie. There were 2 friends who were ignorant. Okay, they were not listening to you. Out of the 2, one stood up and said, hey everyone, let's go for dinner. Okay, so now another one said that, okay, let's go for dinner. Okay, great. Now out of the 2 said that, okay, let's go for dinner. But rest of the 3 said that, okay, this guy has already said that we are going for a movie, and now you are saying that let's go for dinner. And they will say that, okay, Shabir has already said that we are going for a movie. Now the other leader will try to understand that, okay, I have asked for a dinner, but Shabir has already asked for movie night. So let's go for movie only. So that means that everyone is trying to agree to getting a consensus. That means everyone is trying to agree on one single value, one single decision. Okay, you cannot have like, okay, 3 of the friends are going for a movie night and 2 of the friends are going for a dinner night. Everyone should go at one place, everyone should agree on one single decision. So that's what we are trying to get a consensus using the Paxos algorithm. So all the servers, all the nodes of your database within your cluster should agree to single value, should agree to single consistency values across each and every nodes. They cannot say that I have 100 records, another say that I have 40 records and I'm good with it. No, everyone should have the 100 records because maximum value is 100 records. Okay, so that's what the algorithm is, that it works in a 2 phase. That, okay, let's prepare for everyone, let's say what's happening. If everyone acknowledges, propose an idea, and that idea should be accepted. If someone else is asking for the idea, let's give that idea that previously someone has already identified this idea, let's follow that idea only. Okay, now Paxos algorithm is trying to get the consensus. So it has multiple rules, like different nodes will behave differently based on the data. So it has 3 roles available. So one is proposer, second is acceptor, and number 3rd is learner. Okay, proposer is the one who proposes an idea or proposes to prepare for a plan and proposes to accept an idea. That is the leader. Okay, so that's the proposer. Once proposer's idea is accepted, it will be a leader. Acceptor is someone accepting that request and accepting the value the proposer is asking for. And learner is the one who learns the idea, like, okay, what is the idea that was agreed upon and what's the consensus. Okay, now different nodes are available within your cluster, and any of the node can be any of the roles. Okay, so suppose node 1 can be a proposer as well, acceptor as well, and learner as well, and node 2 can be just an acceptor. And later in node 2, if he wants to be a proposer, node 2 can be a proposer as well, node 2 can be a learner as well. So that means that any node can have any number of roles. It is not like that one node can have only one role. Okay, one node can have all the roles as well. So that's the idea behind the different roles and how the roles are defined and what is the actual purpose of the role. So proposer will propose the idea, acceptor will accept those ideas, a learner will learn about those ideas to understand what was the consensus received across all the different nodes. Great. Now, as we understood about the two phases of the Paxos algorithm and the different roles, let's understand how the Paxos algorithm works. Let's consider multiple servers. So let's consider server 1, server 2, server 3. Okay, so here you can see that I have 3 different servers available, 3 different nodes available in my database application system. Now, let me say that this one is my proposer. Okay, S1 has taken the proposer role, S2 has taken the acceptor role, S3 has also taken the acceptor role. Great. Now, out of these 3 nodes, everyone wants to be a leader. As S1 say that, okay, I want to be a proposer, let me propose an idea to be a leader. So S1 will start the phase 1, that is the prepare phase. Okay, so S1 will start the prepare phase. So what it will do is it will prepare a request. So it will prepare a request that, okay, prepare yourself to S2, prepare yourself to S3. So it is sending request to all the different nodes. Now when this request has been sent, 2 things needs to be created. Okay, first thing is that it has to have the ID, that is the identifier of this particular request, and whatever the ID has been sent in this request has to be the greatest value. Okay, greatest value that this proposer, this node has seen. Okay, so suppose there are 4 values that already been seen within this node servers, then S1 should send value 5. Okay, the second thing is it should be unique across the server. So across all the distributed nodes, the value which has been selected to send to all the different servers to prepare for the messages, it has to be unique. Okay, so server 1 and server 2 both cannot send the 5 value. Okay, it has to be unique. So now with these 2 categories, we have identified that, okay, I am sending value 5 to server 2 and server 3. Great. So I'm sending server 2 as prepare for 5, server 3 as prepare for 5. Great. Now server 2 received the message, server 3 received the message, and both identified this thing that, okay, whatever the value that got, which is 5, is greater than the maximum value that I have seen, n. Okay, so they have not seen any value greater than 5 till now. If that's the case, then they will send a promise message. Else they will send a NAK message that it's a negative acknowledgement. We have seen a bigger value than this. We are not promising you the data. Great. So if server 2 and server 3 has seen the latest value as 5, they are promising it. Here they have not seen any value greater than 5. Server 2 saw that 5 value is the greatest. Server 3 also saw that 5 value is the greatest. So both will promise the message. So let's understand that. Okay, so now server 2 send the promise message. Okay, I'm promising. Server 3 also send the promise message. Great. So now server 1 got the data that, okay, server 2 and server 3 promised for value 5. So this is the phase 1. That is the prepare phase. Great. Phase 1 is completed. Now phase 2, that is the accept phase. So now one server 1 received both the acknowledgements, both the promise from all the servers, okay, and this time also it has to get the maximum promises out of all the nodes available. If server 2 and server 3, out of those two, if only one server 2 is sending the promise and server 3 is not sending, then server 1 and server 2 both have sent the promise. Server 1 will also send the promise message to itself, because server 1 can also be an acceptor, as we talked about earlier that one node can have the multiple roles. So 2 promises server 1 got, which is the majority in the server nodes. Okay, so if it got the majority, then it will continue for the next phase. So now we got the majority, all the servers agreed upon the promise. So now let's prepare for the next phase. So in the next phase, what we are trying to do is we are trying to send the accept message that, okay, I'm sending the message to S2 and I'm sending the message to S3. And in both the phase, I'm sending that maximum value is 5 and let's prepare for a movie. Okay, so we are sending the accept message to S2 and S3 that, okay, let's go for a movie, as we have already promised about what we have to do. Now in this case, S2 and S3 will see that, okay, 5 is the latest we have seen till now. No one else has given any of the other values. So 5 is the maximum. Let's accept it. So 5 is the maximum, and then they will accept these values. They will say that, okay, we accept to go for a movie. I accept to go for a movie. And in this case, what it will do is in the accept phase, every node will send the value to each of the other nodes as well. So S3 send the value to S1. S3 will send the value to S2 also. S2 will send the value to S3 also, and S1 will send the value to itself also. Okay, so and S1 will send the value to S2 and S3 as well. So everyone will send the value to each and everyone that I am accepting this value. So at the end, S1 will know that, okay, everyone has accepted the values. So majority of the people have accepted the value that we are going for a movie. Then the consensus is received. Consensus is placed within the entire node that, okay, we are all agreeing upon one value that we are going for a movie. So you can see that the consensus is received within this algorithm and everyone is happy. So this is the happy flow where everyone is good. Great. Now let's talk about the negative flows where it is supposed to fail. And the Paxos algorithm defines that whenever it is failing, the consensus should receive and Paxos algorithm should work as it is. Okay, there should not be any issues within the algorithm. So let's understand the negative flows. So now consider that within this second phase, let me just define this as a second phase. So suppose within this second phase, S3 had a network failure. S3 is not able to connect to rest of the nodes. So in this case, what will happen? Is S3 will not send the message to S1 that this particular message is not done. Okay, that means that only S2 agreed, S3 did not agreed, only S2 agreed and only S1 agreed to itself. Okay, and S1 also sent the message to S2. So that means now what is happening is S1 will know that, okay, out of the three nodes, 2 has given the consensus, 2 has given the acceptance for my movie plan. That means majority of the people has given the consensus. As majority of the people has given the consensus is received with Paxos algorithm and everyone will go for a movie. Great, Paxos works fine here. And whenever this node comes back, they can agree upon the latest value. So whatever the latest value is coming, they can accept that value and S3 will join that group as well. Great, so it was this phase. Now what about acceptor fails as first phase only? So acceptor is not able to send the promise statement from here itself. In the first phase itself, S3 failed and S3 was not able to send the promise here. In this case as well, majority of the people agreed on prepare, right? So majority of the people promised that, okay, I am available. So in this case, out of the 3 servers, 2 of them agreed. So what S1 will do is S1 will send the accept message. It will try to send this also, but it will not reach, but it will send to S2 and it will also send to itself. In this case, we are sending the message that 5 for a movie and S2 will agree to it. Great, S2 will agree to it and S1 will also agree to it. In this case, consensus was received because majority of the people are agreeing to going for a movie. That's great. Consensus is received and everyone is happy. So Paxos algorithm works fine here. So this is the case where you can see that when acceptor fails, everyone is okay, everyone is happy, there is no issue in that. Now let's see the case where proposer itself fails. Okay, so if the proposer fails at the time of sending the first message itself, sending the prepare statement itself, if that is failing, that means that S2 and S3 will not receive any message. If S2 and S3 will not receive any message, then either of the two will decide that okay, let be me a leader, and they will start its own prepare statement and it will try to get the promise from rest of the servers. So S1 is not able to send the message, then S2 will decide that okay, let me be a leader and I will send the prepare message. So it will send the prepare message to S3 and S1. S1 will not receive the message because S1 is not working, proposer is not working. So S3 will receive the message and S3 will say that okay, S3 will say that okay, you are the message, and S3 will say that okay, I am preparing with message 6. Great, okay, because 5 was already taken and the next incremented value would be 6. So S3 will say that okay, I had 6 is the latest that I have seen. Okay, so I will promise to you to accept the message. So S3 will promise and S2 will send the accept message to S3 and S1. S1 will reject it, S3 will approve it, and you can see that the consensus will be received because the majority of the nodes are agreeing to a value. Great. So that's the one scenario. So the next scenario is that post getting the promise. Okay, so let me just define that as well. So what happens is I have sent the message, okay, and what happens is S2 tried to send a message back and S3 tried to send a message back, okay, that you are the maximum and I'm promising the value. But meanwhile what happens is S1 got down. Okay, S1 is not able to receive the messages, S1 is not able to receive the promises, or it's not able to create a new accept message for rest of the nodes. In that case, S2 and S3 will say that okay, we have already sent the promise to S1 and we are yet to receive any message to follow. So they will say that hey, what's happening within the plan, right? We have already agreed upon, we have already promised that whatever you say we will do, and you are not saying anything to us. Then S2 will say that okay, then let me be a leader and I will propose a new message. So S2 or S3, either of them will try to say that okay, let me be a leader. S2 will say that okay, let me be a leader. So S2 will come and S2 will say that okay, I am sending you a message, I am sending you a message, and I am sending you a message with value 6. Great. Now S3 will say that okay, I have previously have seen 5 and now you are 6, so that means you are higher value, I will agree to you. So S3 will agree to S2, S3 will agree to S2, S1 is still down, it's not able to send the message or receive the message, and S2 also send the accept to itself. So that means that majority of the people agreed to value 6. As majority of the people agreed to value 6 for S2, S2 will say that okay, I have now got the majority to accept the message, and then S2 will send the rest of the messages. S2 will send the rest of the messages stating that okay, let me send the accept message, let me send the accept message to each and everyone and let them follow along. So S3 will say that okay, you are the latest one and you are saying for dinner with value 6, let's go for dinner. Great. So here you can see that if P is down, if S1 is down as a proposer, S2 will took over as a proposer and it will send the message and everyone will be happy. Great. Now the other scenario is that proposer P S1 got failed in phase 2. So we saw the scenario where it failed in phase 1. What about phase 2? So in the phase 2, what will happen is, let me just clear everything out. Okay. So what happens here is that S1 has sent the message to S2 and also to S3. Both of them agreed. Okay, both of them agreed the messages to S1, and what S1 will do is S1 will send the message that okay, let's go for movie with value 5. Great. And in this case what will happen is S3 will say that okay, I agree to go for a movie. S2 will also that okay, I agree to go for a movie with value 5. Then S1 got failed. So now S2 or S3 are still waiting that okay, we are going for a movie, but they are not hearing back. Okay, like when are we going for a movie, what's happening? So S2 or S3, either the nodes will try to say that hey, we were planning to go for a movie, what happened to that? So S2 will say that okay, if we are not hearing back from S1 regarding to go for a movie, I have another plan, let's go for dinner. So S2 will now wants to be a leader, and S2 will start a new proposed statement. So S2 will come and S2 will say that okay, let's promise. So it is asking for value 6. Great. Then what will happen is S3 will say that okay, your value 6, which is greater than what I have seen previously 5. So that means that S3 will say that okay, I accept your message. S3 will accept, S2 will accept by itself. Great. S1 is still down. We are not concerned. Majority of the people have agreed. Great. Then what will happen is S2 will say that okay, majority of people have agreed upon the value. I will send the message again that okay, everyone is agreed upon the value, then let's go for dinner night. Okay, now at this time S3 will say that okay, 5 has already asked for movie. Okay, and now 6 is asking for dinner. There cannot be division. Okay, everyone cannot agree to a different value. So what will happen here is, earlier you can see that it has not seen any values prior to this, so that's why they agreed directly. But in this time they have seen that 5 has already asked for a movie. So in return S3 will accept it and will say that okay, you are the latest 6, so that means that I agree to you. Okay, alongside that I will say that you are 6, I agree to you, but I have seen 5 earlier which has asked for movie. Okay, and S2 will get that message that okay, S3 has seen already 5 for a movie, okay, and I have already asked for a dinner. That means that if someone has already asked something earlier, then that means that that is the value that I need to take. I cannot override that value. So S2 will say that okay, as S1 has earlier proposed for a movie, let's go for a movie only. So S2 will get that message and again send a new accept message with a movie. So it will again send a message as 6 with a movie, and it will receive the message, and as both the values are same, they will agree upon that value that okay, everyone is talking about the movie, let's go for a movie. And this way you can see that the consensus will receive across all the different nodes. Okay, so you can see that if you are trying to override the value as well, you should not be overriding the value, you should honor the value which the earlier member of the group has already been told about. Okay, so that's what the entire logic will work about, how the proposer and acceptor are accepting the values. You can see that it is really complex here how the algorithm works, and I'm just talking about the single Paxos here. If you are implementing in the distributed system into multiple nodes, then this will also become more complex. Okay, this is the plain vanilla version that we have talked about. In the industry, when the Paxos has been implemented, it is implemented with the more modifications and more advanced versions as well. So this was all about the Paxos. Now there is still one caveat to it. Here we have already talked about any one of the nodes is trying to be a leader. What if everyone is trying to be a leader? Okay, so let's take the example that we have server 1, server 2 and server 3, and everyone wants to be a leader. Okay, so everyone is sending a message that this send a message to each and everyone with a value 5. Okay, S2 send a message to each one of them with a value 6, and S3 also send a message to each one with a value 7. Okay, so now you can see that everyone is trying to be a leader and everyone wants to be a leader and they want to agree to a value, because in this case what will happen is this entire algorithm will work with all the values. So first it will complete with 5, 6, 7, and at the end everyone will identify that okay, 7 was the latest one and we should agree upon that value and we should do that particular thing. So this will increase the latency as well to get to the consensus where what each of the nodes should do. In this case, to make sure that the latency is decreased and we should get the consensus as soon as possible, we should use the bully algorithm. Okay, now in this case if everyone wants to be a leader, then in this case what will happen is all the servers will emit the latest server value. Okay, server 1 will say that I am 5, server 2 will say that I am 6, server 3 will say that I am 7. Okay, now I am emitting the value to each and every one. If any of the server has seen the greater value than that, whatever it's been received, whatever its value, if they have already get the maximum value, then it will return the maximum value, which means that if server 1 sends the value 5, server 3 will say that okay, your value is not greater than 7, which means I am 7, so I am returning you 7 back. Okay, when S3 sends the value to S2, S2 receives 7 and its value is 6. So in that case S2 value is 6, so S2 will return only 6. It will not return 7 because it's not the greatest value. So at the end, whoever receives the majority with the majority value, okay, that will be the leader. Okay, so you can see that we are trying to get the consensus leader election as early as possible rather than going through all those different phases. So this is an extra modification we have to do as a Boolean algorithm to say that hey, I am the leader, follow me, which will decrease the latency to get the consensus in our algorithm. So this is how the entire Paxos algorithm works. So you can see that it is really complex to implement the Paxos algorithm as well. In the real world, due to the complexity of the Paxos algorithm, it is not majorly used as of now, but this is a stepping stones towards the leader election, and it was introduced in 1989 by Leslie Lamport. Now due to its complexity in implementing the Paxos algorithm, people have now moved to the modern algorithms for leader election, that is Raft. We will cover that in the later section because it deserves its own video, so we will cover in its separate video itself. So now as we have seen the how Paxos algorithm works and in detail like how each and every step will work, its negative scenarios, its positive scenarios and everything, and its complexity, now we should have the deeper understanding that how the leader election works and how when we talk about data replication, database replication or cluster replication, how the leader election is been elected, how the leader is been elected across all the different nodes and how the data is been transmitted. Now there are already libraries available to implement this if you want to, but what I have done is I have just wipe coded this using the ChatGPT and I have taken the normal code out of it. It is a very simple implementation of this Paxos algorithm. This has not been used in any of the production system. It is just for you to understand. Okay, so let's go through that as well so that we can understand whatever we discuss, how it works. So let me go through this, and here you can see that as we talk about the different roles, I have created different files for the different roles. So we have acceptor, we have proposer, and we have learner. So 3 different roles are there. And what is the proposal that we are trying to do? So proposal is a maximum integer number we are taking and the value that we want to get the acceptance from each and every nodes. Okay. So let's talk about the proposer. So proposer wants to propose an idea. Okay. So proposer, it's taking the value and the list of acceptors that I want to send the message to. Okay, so it's taking the acceptors and the value, and it is trying to propose. So whenever it's trying to propose, it's incrementing the number of proposal, that now this is my next proposal, so that we will have the maximum value. And we are defining the majority. So you can see that how the majority will define is m by 2 plus 1. Okay, and m is the number of acceptors. So if you have 3 acceptors, okay, that means your 3 servers, your proposer will also be your acceptor. So out of 3, if 2 is accepting the value, that means it's majority, then you are good. And how many accept counts that you got and the accept values. So what you're trying to do is you are preparing the phase. Okay, it's a prepare phase, first phase. So for each and every acceptor, you are proposing a number. So you are just preparing everyone with a proposal number, whatever the number it is, 1, 2, 3, whatever it is. So you're preparing, and in return acceptor will send either null or any of the value. Okay, so it will send the proposal response, and if it is not null or the value is not null, then we will accept the value and we will continue. Okay, great. If accepted value is not null, so if accepted value is not null, that means that some other value or some other acceptance was already done. Okay, in that case, that will be our proposed value, because if someone else has already proposed some other thing, as we talk about that if Shabir has already proposed for a movie, then someone else cannot say for dinner, we have to go for a movie. So that's what we are doing here. Okay, then it's a second phase where we are proposing the idea. With the proposal number and the proposed value, we are sending to each and every acceptor. And if acceptor is accepting that proposal, then we will increment the counter. Okay, and at the end, if accepted counter is greater than the majority, greater than or equal to the majority, then we will say that we have received the consensus. Otherwise, we need to keep on trying. Okay, so this is a simple proposer code. Let's go and check for the acceptor as well. So in the acceptor, there are 2 phases. There's accept phase and the prepare phase. So in the prepare phase, what we saw is we are sending the proposal number. So in this proposal number, it is just checking that that proposal number is greater than what I have seen earlier. Okay, if this proposal number is the greatest which I have seen earlier, then I will promise to that and I will return true. Otherwise, nothing. And in that case, you can see that it is sending the accepted proposal which has accepted earlier. And in the accept phase, it's doing the same thing. It is taking the proposal and it is checking that whatever the proposal that I am getting, that is greater than equal to whatever I have promised. Okay, if that's the case, then it will accept that proposal and return true. Otherwise, return false. So that's how the entire acceptor and proposer works. So if I go to Paxos simulation, this is the main method that has been written, and you can see that it has a list of acceptors and it has 2 proposer, and 2 proposer are proposing 2 values, value 1 and value 2. So if you run this, you can see that both the values are getting consensus. Okay, so everyone is agreeing to both the values. So this is how the algorithm will work. This is the simplest implementation of the Paxos. This is not to be used in any of the production application. This is just for the learning purpose only. So as a software engineer, you should understand how the leader election works and how this algorithm works. It is really complex and I have tried my best to make it as easy as possible for you to understand. If you enjoy this video and my efforts to make the videos as easy as possible for you to understand, then I would highly encourage that you like this video and subscribe to my channel. That encourages me a lot to work on this awesome videos. So that's been it. I wanted to share with you regarding how the Paxos algorithm works and how it is useful in leader election in data application or server application. It is a state replication system across all the different nodes. It is not just used for the database, it is used for state replication as well. Okay, so ideally this algorithm was for state application, as in the database we already wanted to have the state replicated throughout the different nodes. It was being used in the database application as well. If you have any doubts regarding any of the things that we have covered, then do let me know in the comment section below. I will add the link to this code in the description below for you to check out, and I will see you in the next video. Till then, happy coding. Bye bye.